Alright, ladies and gentlemen, fast recording has started. So today, we are going to discuss acids and bases a little bit, and then get into neutralization reactions. So we'll see how it all, hopefully, how it fits together with this unit by the end of today. So I'm assuming that some of you are familiar, at least with the terms of acids and bases. Yes, you've heard of acids and bases before. Okay. All right. So let's start off with acids. Generally, acids get a negative connotation, right? Because we think about some nasty, like I was warning you about hydrochloric acid over here and stuff like that, you know. But as far as the definition, what is an acid? So, a compound that produces hydronium ions when dissolved in water. That is our definition of what makes something an acid. And as you can see there, this little example equation that shows how an acid sort of comes about. So first, we have to dissolve something in water. That's what goes in B, the little example equation right there, that's what goes in B. First, you got to dissolve something in water. That's what sort of makes it an acid. But when we dissolve it in water, we get that H3O+. Okay? Now, you might say, wait a second, H2O, I know that one. What's H3O? Well, H3O is adding another hydrogen, but you don't add another hydrogen atom, you actually just add a hydrogen nucleus, but without the electron. That's what gives it that positive charge. Okay? And then we're left then with some other negatively charged thing, and that's acid. This one for specific is hydrochloric acid, the one that we were using in the lab the other day. Okay? And we'll find that a lot of things do this when we dissolve them in water. That one of those hydrogens just sort of like plops over and gloms onto the water, and that makes it an acid. Okay? So, some common acids that we deal with here in lab, but also in your house. Hydrochloric acid, nitric acid, sulfuric acid. You'll find them in things like drain cleaners and depending on what kind of like toilet bowl cleaners and stuff like that. But there's also a lot of acids that show up in fruits. When you think like things like citrus fruits and stuff like that have acid in them, the stuff that's in those citrus fruits, when they dissolve in water, they do this. All right, good there? So, how do we know something is an acid? How do we know that this is happening? Well, when this happens, when we dissolve these substances in water and we make this hydronium ion, certain properties develop. First, acids generally have a soury taste. Now, tasting something is not the best way, or should not be the initial test for whether something is an acid or not. Okay, like here, let me take a swig of this and find out whether it has a sour taste. Okay, not the #1 method, but things that are acidic have a sour taste. That things like I said, like citrus fruits, vinegar, these are all acids. That when we dissolve the compounds in the citrus fruit into water, most of the citrus fruits are water anyway, they have that sour taste to them. Okay. Yes, baby.
So, an acid's not technically an acid until it's mixed with water?
Technically, no. Right? Because like hydrochloric acid is HCl, but if you just have one hydrogen and one chlorine bonded together, it's actually a gas. Right? So, but when it gets dissolved in water, that's when that hydrogen here. Let's go ahead here. Okay. When it gets dissolved in water, that's when this hydrogen from the HCl gets like gloms over to that water, and it becomes H3O+. That's the acid, really. Okay? And when that happens, a different set of properties shows up. Okay? HCl by itself is a gas, but when you dissolve it in water, now it has a different set of properties. Does that make sense?
Yeah, so when you said that we were working on hydrochloric acid,
Yep.
that was like the hydrogen chlorine
Hey.
mixed?
Someone ask a question and we just break into conversation. It might be something, you know, you might want to know the answer to. It might show up on the test. Who knows? Right?
It was like mixed with water before we used it.
Right. Yeah. Like that stuff on the table
It's like
mostly is water.
Okay.
Right? Yeah, it's mostly water. We dissolve stuff into it to make it into hydrochloric acid. Yeah. But that's why when you look at most acids are clear. Vinegar is clear, you know, because mostly it's water. It just has a certain chemical dissolved into it, and when that chemical is dissolved into it, we get this H3O plus that shows up, and that's the acid part. Okay? Augustine, go ahead.
What would you consider it before it's mixed with water?
Before it's mixed with water, it's just a compound. That's a molecular compound, right? HCl, two nonmetals, right? You know, so that's just a compound. Like I said, it's a gas, right? And if we drew like Lewis structures, if we drew the dots and the you know valence electrons that surround those atoms, these atoms are stable. They both have, well, chlorine has 8 valence electrons. Hydrogen only has 2, but that's all it needs, right? Okay, and so that it's fine. But when you dissolve it in water, the separation of the hydrogen from the chlorine to glom it onto the water gives it a different set of properties than it had before. Does that make sense? Now, Peyton, that being going back to your discussion from before, when we label hydrochloric acid, we always label it as HCl. Like that's like on that bottle, it would say HCl, hydrochloric acid. Okay? Even though technically the H and the Cl aren't together anymore. Does that make sense? Okay. But that's generally how you label those things.
So if you like wrote the correct way, you wrote it with like that second part of it.
The correct way. This is more of a representation of what is actually going on inside of that bottle. Okay. But you can't have the right-hand side of this equation going on if you don't start with the left side. Okay. Does that make sense? All right. So acids, sour taste. Also, acids will react with metals. And when they react with metals, they generally produce one product along with all the time, and that's hydrogen gas. And you guys saw that in your lab, right? When you added the hydrochloric acid to the zinc, what started happening? It started bubbling, and what were those bubbles? Hydrogen gas, okay? And then finally, and you guys may have seen this before, acids will produce certain color changes in compounds that we call indicators, okay? I'm assuming that most of you sometime along the way, maybe middle school or maybe elementary school, you did a lab one time where your teacher brought in a bunch of foods from home and you got to like touch it to the pH paper and it turned different colors. Anybody ever done that lab before? Wow. Maybe we should do it, yeah. So, anyway, when you do that, there's a chemical in that paper that is sensitive to different acids and bases, and it will turn different colors depending on whether something is an acid or whether it's a base or how strong of an acid it is. Okay? It also happens in nature sometime. Anybody at their house, anybody, either their parents or you, I guess, if you're into gardening, anybody have hydrangeas at their house? Anybody know what hydrangeas are?
I think my mom knows.
No, yeah, so they're pretty common flower here in this part of the country. But you can add things to the soil and it changes the color of the flowers. Sometimes they can be blue, sometimes they can be pink, depending on what stuff you put in the soil, because there is a chemical in the flower that is an indicator. It changes its appearance based on the acidity of whatever we're putting in there. So if you want to have certain colored flowers, you mix certain chemicals into the soil and make it acid, and that changes the color of the flower. If you want it to be a blue or a different color, you put different things in the soil because the indicator changes its appearance based on the conditions that it's in. Good? All right. So on the flip side, from acids, we have bases, right? Much like acids produce hydronia when we dissolve them in water, bases produce hydroxide when we dissolve them in water. again, when dissolved in water. So yeah, so Peyton, going back to like what we did before. This, anybody name this compound right here? Sodium hydroxide, okay? Sodium hydroxide is a white solid. But when you dissolve it in water, that happens, and now it becomes a base. But again, we just label it as sodium hydroxide. But it's actually a solution of sodium hydroxide. If I showed you a bottle of sodium hydroxide, most of the stuff that's in there is water, and there is some sodium hydroxide that's dissolved in that water. That's the base when it dissolves in water. Okay? All right. Calcium hydroxide, sodium hydroxide, magnesium hydroxide. You can see they all end in hydroxide because you need it there in order for it to be a base. Okay. Just like, oh sorry, letter B again is the dissociation, that sodium hydroxide breaking up into the two parts. Okay. Just like acids, when we have compounds that split up and produce this hydroxide, they gain a certain set of properties. So first, bases have a bitter taste. Again, tasting something is not the best, not step number one in determining whether it's an acid or a base, but they do have that taste. For example, things that are bitter, right? Licorice. Yes, black licorice especially. Sorry, black licorice, not Twizzlers. All right. But also too, baking chocolates. If your parents bake, if you ever had baker's chocolate, don't get fooled by that. All right, it looks like a chocolate bar just sitting in the cabinet. It's not a chocolate bar. All right, it's not Hershey's. All right, so yeah, be careful on that. Or if you've ever had Hershey's chocolate powder, you know what I'm talking about? It comes in that canister. Yeah, you're like, oh, I'm gonna make chocolate milk out of this. No, yeah, cocoa powder. Yeah, like I'll make some chocolate milk out of this. No, don't make chocolate milk out of cocoa powder. Right? It doesn't have all the sugar that makes the chocolate taste good. It just has the cocoa, and the cocoa has a base in it, and that base gives it that bitter taste. Okay. All right, good there. Bases also have a slippery feel, like soap, because soap is base. And if you've ever gotten soap in your mouth, right, it has that bittery taste to it as well, right? For you guys, anybody ever see A Christmas Story? Right? You know, when he puts soap in his mouth, you know, yeah. You guys probably don't have to experience much of that now. It's kind of frowned upon in this time and age, but back in the day, that was perfectly acceptable punishment for, you know. So I'm not saying your parents never did it, but you know, it's not as common anymore. So, what even if you're just like in the shower or something, and you're, you know when you're like washing your hair with like all kinds of shampoo, yeah, that's hate it when I wash my hair and soap gets in my mouth. Hate it. So that's a joke. I don't have hair.
Oh, okay.
I don't use
Or if
shampoo.
you're like washing your,
So yeah.
it's like in that area.
And bases will also produce color changes in indicators, but they are different color changes than acids produce. That's how we distinguish one from the other. Let's see if I can find something for you guys. Go ahead, keep writing. This is going to look good if you go watch the recording. Not what I was looking for. Nope. Not what I'm looking for. Anyway, all right. All right. First, anybody have a pool at home or work at a pool where they have to test the water, right? Okay. So the solution that you use to test the water, right? You get a couple of you fill up a little testing device and you put little drops in you put a couple drops in, right? There's something that's like a plastic thing. You fill it up with water. You add little drops to it, and it changes color depending on, and that tells you whether you have to put chlorine in the pool or stuff like that. Yes, no, maybe. So, the little drop that you put in to change the color of the water is an indicator. And like we discussed, indicators are a substance that changes the color based on different conditions, especially in the presence of acids and bases. Is indicators not on there?
No.
Oh, never mind. We'll just talk about it. Okay. So, all right. Litmus paper or phenolphthalein are two common indicators. I just actually, my daughter is doing this little like science like class at LC, just kind of a fun thing, and I don't know if you've ever seen this like magic trick before. It's a quote unquote magic trick. The guy who was doing the class kept changing what drink he was going to drink. He would like start with some water, but then he really wanted some pink lemonade, so he poured it into a different glass and it turned pink. And there was like an indicator in the glass that changes the condition, changes color in the conditions. So these substances will change what they look like depending on the conditions, right? Usually we talk about indicators in terms of acids and bases, but you ever have one of those things that you put your thumb on and it changes colors depending on like how like warm or cold your hand is? Like a mood ring, yeah, what? Or a pencil, like something like that. That's an indicator. It's a thermal indicator, but it's an indicator. It changes its appearance based on the conditions. And we have a lot of those things that we use to sort of describe what's going on and identify if conditions are right for certain instances, for certain things to happen. Okay? All right. Let's talk about the pH scale. Have we heard of the pH scale before? Okay. Short description. The pH scale describes the concentration of hydronium ions in a solution. The pH scale measures or describes the concentration of hydronium in a solution. And remember, hydronium ions are produced by acids when they dissolve in water. So the pH scale is basically telling you what? How acidic something is, right? Because it measures hydronium ions. Okay? pH scale measures the acidity of a solution. Good there? All right. Question that comes up all the time. Okay? Question that comes up all the time. 0 to 14 seems like kind of a weird number, like pick. Why didn't we pick 1 to 10 or 1 to 100? There is a mathematical reason why it runs from 0 to 14. We're not going to talk about why that is. Math-wise, it's a little complex. So we're not going to discuss that. But just know, like when you get to chemistry class, there really is a reason why it goes from 0 to 14. It's just not like a random number. There's actually a mathematical reason for it. So yes.
Why isn't the pH scale?
Okay.
Little c?
All right. That's a good question. So let's do this. Okay. For some background. All right. Okay. Justin, good there? 2 numbers. If I put this in between them, do you know what to do?
Yeah.
Yes. Come on, pen. If I put this in between them, do you know what to do?
Yeah.
Okay. The lowercase p is like that in that it indicates a mathematical operation that you're supposed to perform. Okay? So, the pH, you don't have to know this, okay? The P tells you to take the negative logarithm of the concentration of hydronium or hydrogen in a solution, okay? So it indicates doing a mathematical operation. If I put the little p in front of hydroxide, you would do the same mathematical operation, but on hydroxide instead of hydrogen. Does that make sense? So it just tells you to do a mathematical operation. You don't need to know that for the test or anything like that, but that's why it's the P. It's like a plus sign or a multiplication sign. It just says do a math operation to that value. Okay? All right. Now that we know what the pH scale is, let's talk about what it tells us. Okay? So, pH scale runs from 0 to 14. 7 is the middle of that scale. Sorry, you have a picture like this on the back of your outline. You want to flip it over, you can check the picture out. Okay. 7 is the middle of that scale. That means that if something has a pH of 7, it is neither an acid nor a base. Okay? There's only really one thing out there that, well, actually I shouldn't say that. Pure water, H2O, distilled, nothing dissolved in it or anything, has a pH of 7. When you add things to that water, right, like we talked about, when you dissolve things in water, that makes it acidic or basic. As you dissolve things in the water, it adds either hydrogen or hydronium or hydroxide, and it can change the pH. Moves it either down or up. So you'll see here, if we move to the left of 7 or towards 0, the scale indicates increasing acidity. If we move to the right of 7 or towards 14, we get increasing basicity, right? Which means stronger base, right? So acid and base work sort of opposite of one another. As one goes up, the other one goes down, etc., etc. So lower pH values mean that there is more hydroxide. I know that's a little confusing, right? But that's where, Augustine, going back to our discussion from a little while before, the P represents the negative log. That's how this happens, that as you get more and more hydroxide, you get lower and lower pHs. That's the negative side, okay? Peyton, go ahead.
So, for example, like when you're testing the pool water, what pH level are you looking to have?
I don't have a pool, so I don't know, right? But that's one of the things that they try to do with the testing kit. With the indicators that are in there, instead of giving you a value of the pH, the indicator changes colors depending on the pH. And then, so like, okay, if it's like pink, you have to put something in, or if it's green, you have to put something in,
Yeah, like my dad has like little sticks or things and just spikes in the water.
Yep.
The color I guess changes.
Exactly.
And on the back has a scale. Okay.
Yes.
Yeah.
Those sticks have indicator soaked into them.
Yeah, yeah.
And then as you swipe it, and it changes color depending on the condition, the pH of the pool, and then based on those conditions, you then add stuff or take away stuff or whatever it is. Yeah, but that it's giving you a pH value without giving you a number. It is a qualitative representation of pH as opposed to a quantitative representation of pH. Does that make sense? All right, and then higher pH values mean that there is less hydronium. And that means it is less acidic, but that also means it's more basic. So, we can make different pHs of the same acid. If we go back to hydrochloric acid, one of the very first ones that we talked about on the front page, right? Hydrochloric acid produces hydronium. But if you only put a very, very, very small amount of HCl into the water, there won't be that much hydronium, so you'll have a not as low of a pH. Okay? Good there? And then, at the top of the back page, you have sort of this representation of some common items that are out there and what their pHs are. So you can see that water, distilled water is right in the middle, number 7. It's neutral, it's not acidic or basic. But then, as we move down the line, you can see that a lot of our foods fall into that acidic category. Not too many foods fall into that basic category. All right? So, when you have an upset stomach, one of the things that you can do is drink milk. All right? Milk is closer. You know, sometimes it seems like gross that you want to drink milk when you have an upset stomach, but if you like, you know, if it is like, you know, if you feel like, ugh, sometimes milk will settle it down. Okay? Because milk is pretty close to what on the pH scale? Pretty close to neutral on the pH scale. If you've had a lot of acidic foods, right, and your belly has a very low pH, you can put that milk in it and sort of bring it back more towards neutral. Okay? Now, your stomach is never really neutral. Your stomach is very, very acidic. That's how it breaks foods down. But sometimes you can overdo it, you know, and that milk will bring it back. Okay? Or if you look at Tums or Alka-Seltzer or something like that, if you read the ingredients, Alka-Seltzer, Tums, and things like that always have something hydroxide in them, because if you hydroxide or what's in what? The hydroxide is a characteristic of bases, right? So if your stomach is too acidic, you throw some base in there and it brings it back more towards neutral. Okay? Again, your stomach is never 7 neutral. Your stomach is always very acidic. That's how it breaks things down. But sometimes we can go too close to 0, and that's not what we want. Yeah, you can go close to carbattery acid. You do not want that in your stomach. So, okay. But also too, now, David, good.
What is the 5 mole, or what is the ratio of that 5 mole acid that we use in the lab?
Oh, the 6 molar acid? 6 molar, that 6 molar hydrochloric acid is going to be down here in the 0 to 1 range.
So
okay?
It's not like more acidic than carbohydrates.
No. I mean, it's probably pretty close, right? Again, they're both very acidic, and if you got them on your hand, it would hurt. The biggest thing is that a car battery is kind of big, you know, relatively speaking, compared to the little flask of acid that we had out on the table over there, you know. So if something happens and a car battery explodes or leaks or something like that, you can get a lot of it on you, and that's really the problem. Like getting a little drop of car battery acid, it would hurt, but it wouldn't, like, you know, like I said, it wouldn't dissolve your hand and eat the flesh off of it, you know, just like that hydrochloric acid wouldn't. But if you got a lot of it on, that's when it's a problem. Does that make sense? So, yes, the pH is important, but even something that has a really, really, really low pH, like a 0, even if you just got a drop of it on your hand, it's going to hurt, but it's not going to, like, sustain major damage. Does that make sense? Okay. Augustine, go ahead.
Are there like worse acids than car battery acids?
Car battery acid is pretty bad. Yeah, it's it's pretty bad. Again, one of the things that car battery acid. Okay, when we talk about worse acids, okay, if we want to get morbid for a second here, right? We sometimes think of the idea of like mass murderers who dissolve their victims in like vats of acid. You know what I'm saying?
Yeah.
Okay. Yeah. I hope you don't ever think about doing that, but you know. So, but that's kind of like, you know, like a spooky like stereotypical, you know, mass murderer kind of thing. So, by the way, if anybody's thinking about doing that, come talk to me. We'll get you like we'll talk to the counselor. All right. So,
If you're gonna tell them how to do it.
yeah, I'll make sure you do it right. So that was a joke. If anybody's watching the video, so.
Oh yeah, I forgot.
That was a joke. In case you're watching the video. So. I'll take you to the counselor, and we'll discuss why you want to put people in vats of acid. Okay, and see if we can get that straightened out. All right? So Augustine, in that case, Augustine, I'm addressing it to you as if you're thinking about doing this, but anybody. In that case, it's not really so much the strength of the acid; it's how much acid you have, right? That's really that. Those acids would be strong. A big vat of acid would be strong, but it's no stronger than that flask of hydrochloric acid that we had on the table the other day. Maybe a little bit stronger, but not significantly. It's just a matter of the amount. Right? Does that make sense?
So, could it be like any base could do that?
Say again?
I mean, acid, could like any acid?
So the question was, could any acid do that? And the answer is, yeah. It just depends on how much of it you have, right? Certain acids, like vinegar is around 2.5, so it's acidic, but it's not real acidic. Even if you had a huge vat of vinegar, it's not gonna it would be gross, but you could swim in a huge vat of vinegar, right? It might irritate your skin, but it wouldn't like dissolve your flesh because the pH isn't that lower. But vinegar is acetic acid. If you had very concentrated acetic acid, that could do it. Right? So vinegar is not so much about what it is, it's more about the concentration of how much acetic acid is dissolved in the water. We have, acetic acid is like the stinkiest, it smells like vinegar, but it's like super, super strong because it's so concentrated. Like we have a cabinet back there, it says acids on it, and if there's acetic acid, we have a bunch of them around here, but if there's acetic acid in it, every time I open up the cabinet, I'm just like, oh, it just like hits you, it's like, what?
No.
I know, it's weird.
Moonshine.
It smells like vinegar, but like a really, I don't know.
Yeah, it's really strong vinegar. Like that's what it is. And this is 9 molar, right? So it's pretty concentrated.
What if you put baking soda in it? Would it go like even crazier than? What if you put baking soda in it?
That smells actually good. I would. No, that's vinegar is great.
Augustine, I took that as like a challenge. I actually have. So just so you guys know, I actually have baking soda in here because Wednesday when we were doing the lab, the next class, somebody was doing that station. They moved the flask and they hit it on the sink and it just like shattered. Like the hydrochloric acid thing just shattered. Most of it went in the sink, but some of it was on the table. So what do you do when acid gets spilled on the table? See where baking soda is? Baking soda is on the basic side. So, and actually, that's kind of a good lead-in to where we're going next. So we'll talk. Actually, this is a good lead-in. We'll go here, right? So, baking soda, as you can see from the pH scale, 8.5-ish on the pH scale, right? Okay, so we'll put some in there. Ooh, that's kind of a lot. That's all right.
Like when you do the baking soda,
Yeah.
that's like you put a thing of, you put like baking soda in your mouth and then you just like explode. That's disgusting. And then you just, I've done it.
Has anybody ever done this? Like when you made, did anybody like make a volcano for the science fair back in like 3rd grade or whatever? So, disappointed.
We did.
I never had it.
We did it for a project. We were doing landing ones.
All right. I don't think you're gonna be in the splash zone. So. All right. So instead of pouring this acetic acid straight from this big bottle, I'm gonna get a smaller.
I didn't choose where to walk to Central.
It's like south of Mexico.
Oh, I forgot America's pumpkin.
Acetic acid stinks.
It smells
Everybody.
like salt and vinegar chips.
I have
There's
the
vinegar.
worst,
Well,
so I can't smell.
All right, here we go, everybody.
Watch your eyebrows.
All right, ready?
Ooh.
I don't want it to go all over the place, you know, just because I don't want it to.
if you touch that, would it like hurt?
This would hurt the acetic acid would hurt your hand a little bit, right? That, no, because what am I mixing in there?
A base.
A base with an acid, right? And that's where that's the next slide we're gonna talk about in a second here.
Okay. But like that right there, like that you put
Oh, perfect.
like for more than the hydrochloric acid.
Yeah. Depending on how much you got on your hand, obviously, you know, so.
Mr. Clements,
Yeah.
what would happen if you mixed car battery acid with drink?
What's the
So,
ratio?
actually, well, Augustine, that's a great lead-in, Augustine. Thank you for bringing that up. So just so we make the transition, right? Why did you ask about car battery acid and drain cleaner?
Because it's the most basic and most acidic.
Okay, so when you mix the most basic with the most acidic, what are you going to end up with?
Like neutral.
Something neutral, right? So when we mix acids and bases together, we get what we call a neutralization reaction. Okay? So neutralization reactions are a double replacement reaction between an acid and a base. Double replacement reaction between an acid and a base. So first, that's why we put this here in this unit, a double replacement reaction. Do we remember what happens in a double replacement reaction? They're good. Well, we start with two bonds.
I know how.
We start with two compounds, right? And then what happens in your two compounds? We like switch fronts and backs, right? Switch cations and anions, right? So, then what? Yeah, I'll put it in.
No, just leave it. I like it.
You're one of those weirdos that like salt and vinegar chips, aren't you?
Yes.
People who put vinegar on their French fries.
What? Like just get like a tub of vinegar and you just dump.
Yeah.
A vinaigrette.
All right.
Or like, yeah.
I mean, it's basically the same thing.
So good. Like that's why
That's like my daughter. My daughter hates spaghetti sauce. Like she's like, I don't like spaghetti sauce. She doesn't eat pizza that has sauce on it, but then she put ketchup on everything. Like you realize it's the same thing, right? So.
Does she like
All right.
tomato
like
soup?
What?
Does she like tomato soup?
No,
It's like
no,
not
she
like
does not like tomato soup.
French fries.
So
It's like
But
it's just
she likes ketchup. So anyway, all right. So just like it says in double replacement reaction, cations and anions are replaced or flip around, and they form an ionic compound called a salt. But something that is characteristic of a neutralization reaction is that it always produces water. Okay? So let's take a look at a couple. You have a couple down there on your sheet. Those are the ones we're going to take a look at. Okay. All right. So here's the neutralization reaction between hydrochloric acid and sodium hydroxide. Okay. Which one's the acid? I know I just called it that, but which one's the acid? HCl, and we know that because it starts with what? H. Right? Things that generally have H at the beginning are going to be acids. And then the other one is a base, because what does it have at the end? OH, right? Bases produce hydroxide. So, that being the case, the H is at the beginning of this compound, the sodium is at the beginning of this compound, the chlorine is at the end of this compound, the hydroxide is at the end of that compound. Okay? Double replacement. We flip fronts and backs. What is sodium going to end up with from the other side? Fronts, cations joined together with what? Anions. What's the anion in HCl? Cl, right? So Na and Cl are going to end up together. Okay? Does that make sense? But then,
H2O.
on the other side, the H here ends up with the OH over here. H and OH is
H2O.
H2O, right? Sometimes you'll see it written this way to show the hydrogen and the hydroxide coming together, but in the end, it's really just H2O. And, as we learned before, what's the pH of water? 7. It's neutral. Okay. Good there? All right, let's take a look at this one. So, what? Yeah, that's salt water. Yep, that would just be salt water. It would taste salty. You could drink it because now, sorry, Now, one thing you have to keep in mind, okay, and we'll talk about this a little bit more next week. You would end up with salt water as long as you had an even amount of HCl and NaOH, right? If you had a lot of HCl and just a little bit of NaOH, would you make salt water? Yes, but do you have enough NaOH to neutralize all of the HCl? If you have a lot of HCl and just a little NaOH, you'd make a little bit of salt water, but there'd still be a lot of HCl left over. Okay? Yeah, go ahead.
So what if HCl is like a much stronger acid than NaOH?
It's not, but that is an issue, right? That we don't have acids that NaOH is just as strong of a base as HCl is an acid. Just it is, okay? But that's not always the case. Could we neutralize a strong acid with a weak base? Yes, you could, but you'd have to add more base to make sure that you get all of the acid neutralized. So yeah, there's two factors. One is the pH of each solution, but also the other one would then be, okay, how much of each solution do I have? Okay? All right, so here's the second one, right? Okay? I'll show you the products and then see if it makes sense. Okay, ready? Here we go. Does that make sense where those products came from?
Oh yeah, no.
Because it's a double replacement reaction, right? So the magnesium over on the second reactant, first, magnesium hydroxide, acid or base? Base. This is a base because it has hydroxide in it, right? Okay. The magnesium here is going to join together with the anion over here. That's why magnesium and nitrate end up together.
I said there's two substrates.
Ah. So, Augustine, do you remember off the top of your head what charge magnesium has based on its position on the periodic table? So turn around and can you read the periodic table on the back and see magnesium? Okay, so what charge is it going to have?
It's a cation.
Yep.
So it will have a negative.
Nope.
Positive.
How many positives based on where it is on the periodic table?
1 or 2.
You tell me which one.
2.
2, okay. So, that being the case, remember that nitrate is one of those polyatomic ions, right? Okay. What charge will it have based on that formula? Someone can help Augustine if you want. If magnesium has a +2 charge,
I'm going to say negative.
negative,
It's going
good.
Yeah.
Okay. How many negatives?
2, 1.
How many nitrates are there in that formula?
3.
There's one nitrate.
In this compound, in the product over here. Okay? This magnesium brings with it +2 charge, right? How many nitrates are there here? 2. There's 6 oxygens, but there are 2 nitrates. So what does the charge on each nitrate need to be? -1, because it's got to balance out. Yes, no, maybe? All right, good there? It's okay, it can be no, that's all right. That's pretty advanced stuff. So it's, okay. All right, that's good for today. We'll start in on the quantitative relationships on Monday. There is a little bit of homework, just a couple questions about neutralization reactions from the book.